Every single day, we witness phenomena so fundamental, so inevitable, that we never even think to question them. Think about it. A glass of water spills on the floor and the water spreads out, but we never see it gather itself back into the glass. An ice cube melts in the warm sun, but that puddle of warm water never spontaneously refreezes into a perfect cube. An egg drops onto the floor and shatters, yet no force in the universe can reassemble the shell and its contents back into a single, pristine egg. A lit candle burns down its wick and melts its wax, but that process never reverses itself. And most personal of all, memory. We can clearly remember a conversation we had yesterday, but we will never be able to remember a conversation we're going to have tomorrow. These events, which we take for granted as simply being part of life, all have one thing in common. They only move in one direction. They are tangible proof of something incredibly fundamental about our universe, a rule that is never, ever broken. This rule, which traps us all in a relentless march from the past to the future, is known in physics as the arrow of time. We live in a world dominated by the arrow of time. This invisible cosmic river carries us all forward, ceaselessly, from one moment to the next. We can record an event, play it in reverse, and watch the spilled water go back into the glass, but we know that's just an illusion. It's the inverse of our reality. Why is our reality so unforgiving? Why is the arrow of time so powerful and so absolute? Why does the universe seem to have an unwavering preference for moving forward? This simple question is one of the greatest mysteries in all of science. It has baffled some of the greatest minds in history. Albert Einstein himself, who reshaped our understanding of time, once said that the distinction between past, present, and future is merely a stubbornly persistent illusion. And yet, for those of us who live and breathe, that illusion feels profoundly real. Modern physics offers two surprising answers. The first, and most famous, is entropy, the universal law that states everything tends to move from order to chaos. An ordered ice cube becomes disordered water. A structured glass becomes disordered shards. Every event in the universe, from a star exploding to a memory fading, is an act of increasing entropy. But this is where the mystery deepens. What if I told you that the arrow of time we experience doesn't exist in the most fundamental laws of physics? The laws that govern the motion of particles, atoms, and molecules, from Newton's laws to quantum mechanics, are mathematically time-symmetric. That means, in theory, if you were to play a film of how these particles interact, their motion would look perfectly plausible, both forward and backward. So why is our macroscopic world, which is made up of these very particles, so incredibly asymmetrical? This is one of the biggest paradoxes in all of science, a loophole in the very foundation of our understanding of reality. The arrow of time is not just a property of the universe, but a mystery that challenges us to ask, is there something fundamental we are missing? Is there a way, however small, that might allow us to peer back into the past? The answers to these questions will take us on a journey that not only crosses space and time, but also to the deepest frontiers of human knowledge. To truly understand why time has only one direction, we have to dig a little deeper into the fundamental laws of physics. And there, we'll find a concept that governs everything from your cup of coffee to the ultimate fate of the universe itself. That concept is entropy. So what is entropy? In a nutshell, entropy is a measure of disorder or chaos within a system. It's a concept that's easiest to understand through simple examples. Imagine you have a room you've just cleaned. All the books are neatly on the shelf, your clothes are folded in the closet, and there's not a speck of dust on the floor. This is a state of low entropy, because everything is in a highly ordered state. Now, imagine you spend a week living in that room, reading books, trying on clothes, and eating snacks. Naturally, without any effort, your room will become a mess. Books will be scattered, clothes will pile up on chairs, and crumbs will be on the floor. Your room has reached a state of high entropy.
There's no magic here. It's the natural tendency of the universe. And this tendency is summed up in one of the most powerful laws in all of physics, the second law of thermodynamics. This law states that in an isolated system, meaning no energy or matter is entering or leaving, the total entropy always increases over time. Systems will always move from a more ordered state to a more disordered one. Take another example, a beautiful sandcastle on a beach. You've spent hours building it with its perfect, intricate spires. This is a state of very low entropy, but over time the wind will blow, The waves will come in and maybe someone will accidentally step on it. Slowly but surely, that sandcastle will crumble and reintegrate with the sand around it. The sand grains that were once in an ordered formation are now scattered randomly across the beach. Entropy has increased. Now ask yourself, have you ever seen the wind and waves perfectly reassemble scattered grains of sand into a perfect sandcastle? Of course not. It's not theoretically impossible. If every grain of sand were to move in the exact right direction and speed at the exact same time, a sandcastle could reform. But the probability of that happening is so incredibly tiny it's practically zero. It's less likely than winning the lottery 1,000,000,000 times in a row. And this is where we find the origin of the arrow of time. Time moves forward because it's the most statistically probable path for the universe. Every event, from a cup of coffee cooling down to a supernova exploding, is a step towards increasing entropy. Time is a consequence of this statistical law. We experience the flow of time as a one-way street because the odds of seeing it go in reverse are infinitesimally small. The more particles involved in an event, the more entropy is produced and the more impossible it is for that event to reverse. From the macroscopic scale, like a melting ice cube, to the cosmic scale, entropy is the ultimate driving force. Our sun, for instance, is a low-entropy system, concentrating energy and radiating light and heat into space. As the sun burns its fuel, it spreads that energy out into the universe, increasing entropy on a massive scale. When it finally dies and becomes a cold white dwarf, entropy in the universe will be higher. The entire universe itself, according to this view, is a giant system moving towards a state of maximum entropy, where all energy is evenly spread out and nothing else can happen. This state is known as the heat death of the universe. So the arrow of time, which feels so real and inescapable to us, is a manifestation of the universe's tendency toward chaos. It's not a rigid law, but a statistical consequence of the sheer number of particles interacting. But this raises an even stranger question, which we'll get into next. If the flow of time is a result of statistics on a macroscopic level, why do the fundamental laws that govern individual particles have no time direction at all? Why in the smallest of worlds can the laws of physics run both forward and backward? This is a mystery that opens a crack in our understanding of reality. We've established that the inescapable arrow of time is a consequence of entropy, the universe's tendency toward chaos. A glass shatters into 1,000 pieces, not the other way around, because the shattered state is statistically far more probable than the whole state. This is a powerful explanation, and for many it's enough. But this isn't the end of the story. It's the beginning of a much deeper mystery, a profound paradox that has baffled the world's greatest physicists for over a century. The paradox is this: our universe as a whole is fundamentally asymmetrical in time. And yet, when we look closer at the fundamental laws that govern individual particles, we find something truly bizarre. These laws, which are the very foundation of all reality we see, have no preference for time at all. They are fundamentally time-symmetrical. Let's imagine a film. Not a film about a billiard ball, but one about something far more fundamental. Think of a hydrogen atom and its orbiting electron. The laws of quantum mechanics that govern their motion and interaction work precisely the same way whether you play the film forward or backward. Nothing looks out of place. The forward and reverse movements appear equally logical and valid. The laws of gravity are the same. A planet orbiting a star would look no different if you played its journey in reverse. Even electromagnetism, light, magnetism, everything that makes electricity possible, works perfectly both forward and backward in time.
This is a gaping hole in our understanding. If all the particles and interactions on the smallest level don't care about the direction of time, why are their aggregates, us, galaxies, the entire universe, bound to an inevitable flow of time? Where does the arrow of time emerge from? This is the very question that drove Ludwig Boltzmann, a 19th-century Austrian physicist, to the brink of despair. He realized that heat flows from a hot object to a cold one, not because the law forbids it from flowing the other way, but because there are infinitely more ways for energy to be spread out, high entropy, than to be concentrated, low entropy. Boltzmann argued that the arrow of time is not a fundamental law, but a consequence of the universe's initial conditions. If the universe began in a state of incredibly low entropy, a highly ordered state, then the inescapable arrow of time is simply its journey toward its most probable state, utter chaos. But Boltzmann's answer brings up another problem. If the arrow of time is merely statistical, then theoretically, there should be statistical fluctuations where entropy decreases, even if for a very brief moment. That means somewhere in the universe, a glass should spontaneously reassemble, or a particle could return to a more ordered state. But we never observe this, not even on a quantum level. This haunting mystery led some physicists, like Albert Einstein, to theorize that the distinction between past, present, and future is merely an illusion. But how can we accept that idea when we are so profoundly trapped in time's constant flow? This paradox shows that the arrow of time we experience is not a rigid law like gravity, but a puzzle that emerges at the intersection of our microscopic quantum world and our macroscopic world. It is a deep hole in our understanding, a sign that we may not have the full picture of how the universe works, and therein lies both its beauty and its terror. The arrow of time might not be part of the game's rules, but a result of how we're playing it. The question now is there a way to control the game? And is there, beneath all of this, something that truly creates time itself? This is the question that will lead us to the very edge of physics and into the strange world of the quantum. If entropy gives time a direction, ensuring it moves from past to future, then relativity gives it flexibility. Up until the early 20th century, everyone, including the greatest physicists, believed that time was a constant, universal flow, the same for everyone everywhere in the universe. It was a notion that was never questioned. But then, a young man named Albert Einstein came along, and with his two revolutionary theories, he shattered that idea, forever changing our understanding of time. Einstein taught us that time is not a universal constant, but a dimension, woven together with space, to form a single fabric called space-time. And just like a fabric, space-time can be bent, stretched, and affected by two fundamental forces: speed and gravity. This is what's known as time dilation. Let's explore the first phenomenon: velocity time dilation. The simple rule is, the faster you move, the slower time runs for you. To understand this seemingly impossible idea, let's use the most famous example: the twin paradox. Imagine a pair of identical twins. One twin stays on Earth while the other gets into an incredibly fast rocket that can travel at speeds close to the speed of light, and they go on a long journey through space. For the traveling twin, nothing feels out of the ordinary. Their clock ticks as normal. Their heart beats at a regular rate. Time is business as usual, but from the perspective on Earth, the clock on that rocket is running much, much slower. When the rocket finally returns to Earth, what happens? The traveling twin may have aged just 10 years, while the twin who stayed on Earth has aged 50. They don't just look different. One is physically and measurably younger than the other. This isn't science fiction. It's a real consequence of Einstein's theory of special relativity. This phenomenon has been proven multiple times with incredibly precise atomic clocks flown on jet planes and even on GPS satellites. These clocks show a tiny but real-time difference, proving that motion does in fact affect the flow of time.
But speed isn't the only factor. There's another even more powerful one: gravity. This is called gravitational time dilation. Einstein theorized that the mass of an object warps space-time around it, just like a bowling ball placed on a stretched trampoline creates a curve. This warping of space-time is what we experience as gravity, and near a deeper curve, time runs slower. If you are on top of a tall mountain, time runs slightly faster for you than for someone at sea level, simply because you are a tiny bit farther from the Earth's center of mass. The difference is minuscule on the scale of nanoseconds, but it's so real that modern GPS systems have to account for this effect. Without this correction, our global navigation system would have a daily error of several miles. Now imagine this gravitational time dilation near an object with extreme gravity, a black hole. There, space-time is warped so drastically that time almost comes to a standstill. If you were to watch a black hole from a safe distance, you'd see an astronaut approaching its event horizon slow down, and eventually appear to freeze in time, never truly crossing it from your perspective. However, for that astronaut, their clock would keep ticking normally and they would cross the event horizon in a flash. In the most extreme example, if you could stand near an ultramassive black hole like TON 618, a few minutes for you might equal billions of years on a distant planet. You could watch the entire life cycle of a galaxy, from its birth to its death, in the blink of an eye. Both speed and gravity affect time, and they both work together. Beneath all of these theories is an incredible understanding. Time is not a straight, constant line, but a river that flows at different speeds in different places, shaped by our own motion and the gravitational fields around us. It's a reality that makes us feel small, but at the same time, gives us a bigger picture of the intricate cosmic dance. Yet even with all this flexibility, one thing remains constant. Time still only moves forward. Time dilation just makes it run slower, not backward. And that's where the deepest mystery lies. If relativity can't reverse the arrow of time, could the answer lie in an even stranger set of laws? Perhaps the answer is in the very small, where the fundamental rules are broken. We've seen that entropy gives time its direction, and relativity makes it a flexible concept, one that can be stretched and bent. But all of these theories have one thing in common. They treat time as a variable that already exists. But what if time itself is an illusion, a side effect of something far more fundamental? To answer this question, we have to leave the universe as we know it and jump into the strangest, most chaotic world of all, the realm of quantum mechanics. In this incredibly small world, the world of subatomic particles, the laws of physics we take for granted simply don't apply. Here, a particle can be in many places at once. An electron can be spinning up and down at the same time. This isn't just a metaphor. It's a fundamental property of reality on the smallest scale, known as superposition. Imagine a coin spinning in the air. Until it lands, it isn't heads or tails, it's a combination of both. That's how particles exist in the quantum world, in all possible states simultaneously. In this world, nothing is certain, nothing is deterministic. We can't predict where an electron is going to go. We can only calculate its probability of being in one place or another. It's a blurry, chaotic universe governed by chance, not certainty. And this is where we find a candidate for the ultimate origin of the arrow of time. According to the standard interpretation of quantum mechanics, this superposition ends when a measurement is made. When we observe a particle, we force it to stop existing in all possible states and choose a single one. This moment is called the collapse of the wave function. In an instant, all other possibilities disappear, and the particle takes on a single definite identity that is now part of our reality. Some physicists believe that this is the true moment of time creation. Every collapse of the wave function is a one-way, irreversible event. It's a decision the universe makes, pushing it forward. Every time an atom interacts, every time a photon hits something, every time a measurement is made by a piece of equipment or even by another particle, a new piece of history is created, and we can't go back to the previous state of superposition. This process is the very essence of the arrow of time on the most fundamental level. This theory also leads us to another mind-bending mystery called quantum entanglement. Imagine two particles are created together and become linked. No matter how far apart they are, even on opposite sides of the galaxy, if you measure one particle, the other will instantly take on the opposite state. This is the spooky action at a distance, as Einstein called it. This mystery leads some physicists to speculate that entanglement might be key to understanding how time emerges. Some even suggest that time may not exist at the most fundamental level at all, but is instead an emergent property of the complexity and relationships between trillions of interacting particles. If that's true, then time isn't a flowing river. It's an illusion created by the collective interaction of particles that have no time at all. We experience it because our brains, made of billions of particles, organize incoming information into a linear narrative. It's an incredibly radical thought. Maybe the arrow of time isn't about why we can't go back to the past, but about why a past even exists in the first place. So from all the clues we found, from entropy to relativity and quantum physics, the answer remains blurred. We have a thermodynamic arrow based on statistics. We have a relativistic arrow that slows time down, and we have a quantum arrow that may create time itself with every observation. What we've discovered is that time is not one simple concept. It's a multi-layered, confusing puzzle. But within that mystery, there's also a realization. We aren't bound to a cruel, unchanging arrow of time. Instead, we are part of the process. We are the witnesses and maybe even the creators of its flow. And in this mystery, we find not darkness, but a profound beauty. We have traveled a long way, from a simple spilled cup of coffee to the mind-bending realities of space-time and the chaotic, probabilistic world of quantum mechanics. We've seen how entropy pushes us relentlessly forward. We've learned that relativity can bend and stretch time, but never break its forward momentum. And we've pondered whether the very act of observation creates the flow of time itself. It's enough to make you feel a little lost in the vastness of the cosmos. But there is a different way to look at it. What if the arrow of time is not a prison, but a profound gift? What if its unyielding one-way journey is not a bug in the system, but the very feature that allows for everything beautiful and meaningful to exist? Think about it. Without a consistent flow of time, there would be no causality. No cause and effect. The universe would be a static, unchanging, frozen mess where nothing ever happens. Stars would never be born or die. Galaxies would never evolve. There would be no stories, no memories, no growth. The arrow of time is what gives the universe its grand cosmic narrative. It is the framework that allows for beginnings and endings, for learning from the past, for hoping for the future, and for the very concept of consciousness to take root and flourish. The fact that things can break and never fully unbreak is what makes our actions, our choices, and our existence matter. So in the face of this profound mystery, we find a deep and beautiful truth. The arrow of time is not a curse. It is the very reason for our existence. It's what gives life its meaning. It is the fundamental force that allows for every single moment we cherish to be unique, unrepeatable, and forever etched into the story of the universe. The story of time is just one of the many mysteries that exist in the universe. And here at Knowverse Science, we're dedicated to unraveling those secrets for you. If you were captivated by these incredible facts and want to keep exploring the frontiers of human knowledge, there's so much more waiting for you. From the secrets of dark matter to the search for life beyond our planet, we'll continue to bring you the most amazing science stories. So don't miss out on our next adventure. Subscribe now and hit that notification bell so you never miss a new video. Let's keep exploring together.